Lesson 5.4 notes, proving theorems on isosceles and equilateral triangles. As a refresher, an isosceles triangle has at least two congruent sides, called legs. The non-congruent side would be called the base. The angles around the non-congruent side are your base angles, and the top angle would be our vertex angle. The first theorem that we're going to prove states that if a triangle is an isosceles triangle, then the base angles of the triangle are congruent. We have this figure given, and so our given would be that triangle ABC is isosceles with AB congruent to BC. Our job then is to prove that angle A is congruent to angle C. Our first step in any proof will always be our given, so we have that step in there. Our overall plan for this proof will be to create a pair of congruent triangles and use CPCTC to get the two angles A and C to be congruent. So to do this, let's create a midpoint of the segment AC. We're allowed to do that because every segment has a midpoint. Once we've done this, we can use the definition of midpoint to have AD congruent to DC. This allows us to separate our triangle into two smaller triangles and prove that they are congruent. We're allowed to draw this line because 2 points always determine the line. Once we've drawn the segment, we can say that it is congruent to itself using the reflexive property. This gives us SSS to prove our two triangles congruent, which allows us to use CPCTC to state that the angles are congruent. So the next time that you need to say that the angles of an isosceles triangle are congruent, you can simply say isosceles triangle theorem. Now let's move on to the converse of the isosceles triangle theorem. Think about what you know about a converse and how to write that. Take a second and try to fill in the blanks. The converse reverses your hypothesis and your conclusion. So what you should have is a statement similar to this. If two angles of a triangle are congruent, then the triangle is isosceles. This is what we're going to prove. Let's start by drawing a diagram. Since we are given the fact that the two angles are congruent, that's all we can label on our figure. So here, our given would be that angle B is congruent to angle C. What we're trying to prove is the statement that the triangle is isosceles. Our general procedure is going to be the same, and that would be to create that bisector in the middle and use congruent triangles and CPCTC to be able to state that AB is congruent to BC, making the triangle isosceles. But since we already did a midpoint on the last proof, this time let's use an angled bisector. So what we're going to do is add D so that AD would bisect angle BAC. Now we can use the definition of bisect to state that angle BAD and CAD are congruent. The rest of this proof should be very similar to the last proof. Stop the video and try to finish the proof on your own. Once you've completed it, turn the video back on and see how it compares to the proof I've done here. Take a look at the proof, compare it to yours, and make any adjustments necessary. Hopefully you caught that this time we used AAS because we had that second pair of angles rather than sides. Let's move on to the next proof. The next theorem we'll be proving states that if a segment bisects the vertex angle of an isosceles triangle, then that segment will be a perpendicular bisector of the base of the triangle. So we're given that the segment BD bisects angle ABC and that triangle ABC is isosceles. Our job is to prove that AD is congruent to CD and AC is perpendicular to BD. That will allow us to state that it is a perpendicular bisector. Let's start by proving the two triangles congruent. Stop the video and get that far in your proof, and then resume the video. Hopefully you have something like this proving that the two triangles are congruent. We can now use CPCTC to get the two segments at the bottom, AD and CD, to be congruent, as well as angles ADB and CDB. So we said that these two are congruent by CPCTC. On our figure, that's going to look like this. We have not yet proven that the angles around B are right angles. In order to do that, we're going to need to use the linear pair theorem to get them equal to 180 degrees together, and then use that fact and the fact that they're congruent to go through and simplify to get the angles to be 90 degrees. Here's what that looks like in the proof. Since we're going to be using angle measures, we need to jump into the fact that those angles, their measures are congruent. We set this up using the linear pair theorem, and then we can use substitution to make them the same angle. Now we have that angle ADB is 90 degrees, which allows us to state that that AC and BD are perpendicular to each other. Now that we've proven that both AD is congruent to CD and AC is perpendicular to BD, we can now refer to BD as the perpendicular bisector of AC. Whew! Good news is that's the longest proof in this set of notes. The final two proofs are a little bit shorter, a little bit easier to follow. Let's take a look at the next one. Since the definition of an isosceles triangle says that it has at least two sides congruent, an equilateral triangle is really just a subset of an isosceles triangle. So these are going to be corollaries, which are easily proven using other theorems. And what we're going to do is prove the corollary to the isosceles triangle theorem, and then we're going to flip it around and prove its converse. So let's start with the first one. If a triangle is an equilateral triangle, then it's also equiangular. So what we're given here is that the triangle is equilateral. What we have to prove is that it's equiangular. Start by filling in your givens. Since we use the term equilateral in our given, let's determine what that means. What it means is that all three sides are the same. So we can say that EF is congruent to FG, which is congruent to EG, using our definition of equilateral. Based on what I said earlier, we can also call this triangle isosceles because it does meet the definition of isosceles, which will allow us to choose any two sides as and use our isosceles theorem to get their opposite angles congruent. Let's follow how that works. I have E congruent to F using my isosceles angle theorem. Since I have three sets of congruent sides, it's a good idea to emphasize what you're using, which is why I said that I'm using the fact that EG is congruent to FG. We can also say that angle F is congruent to angle G. See if you can write the reason for that. Now we can use the transitive property to pull all three angles together and the definition of equiangular to finish off our proof. And this is what your proof should look like. Again, I want you to think of a converse. If we're going to do the converse, we need to flip things around again. So the corollary to our converse would read, if a triangle is equiangular, then it's also equilateral. See if you can do this proof on your own. Stop the video, give this a good shot, and then turn the video back on and compare it to mine. We start with our givens and use the definition of equiangular to get all three angles congruent. This time, since we're going backwards, we're going to have to use the converse of your isosceles angle theorem, not the isosceles angle theorem itself, to get the sides from the angles. I've done that with EF congruent to FG and then FG congruent to EG. You can choose any pairs you want as long as you include all three. Once you have all three, that leads you to your transitive property to get all three congruent to each other, which is our definition of equilateral. Therefore, the triangle would be equilateral. This concludes the proofs in this lesson. Move on to your online math Excel work, and we'll see you in class.